Hi guys, I hope you're doing well. So today we're gonna finish chapter 7. Um, I'm gonna talk about a normal approximation to binomial distribution. So remember guys, we said a binomial distribution is actually a discrete distribution, okay? But the idea now is to use the central limit theorem. Remember guys, central limit theorem can be applied to either continuous or discrete distribution, okay? So we can apply central limit theorem to approximate binomial distribution. Okay, so let's start first with binomial distribution. So let's consider a binomial distribution. So remember, so we have n, that's the number of trials. P, that was the probability of success. Okay, and we had Q, that's probability of failure. Okay, and remember guys, P and Q adds up to 1. So P plus Q are equal. So P plus Q is equal to 1. And then we have R, that's the number of successes. Okay. So as I said, so we have a binomial distribution, then we're going to use a central limit theorem. The thing is, so if n times p is larger than 5 and n times q is larger than 5, then actually we can approximate the binomial distribution by a normal distribution. Then the r, the number of successes, has a binomial distribution that's approximately normal. Okay, so it's approximately a normal distribution. Okay, with the average or mean mu equal to n times p and standard deviation sigma equal to square root of n times square root of npq. Okay. There is only one thing, guys, here. There is a correction, because binomial distribution is supposed to be discrete, okay, and a normal distribution, it's a continuous distribution. So there is a correction for continuity here. So when you say correction for continuity, if you say continuity, okay. So if we say, for example, if you want to find a probability that the number of successes is larger than or equal, let's say. So if you want to find probability of that the number of successes is equal to A, okay, then if you want to use a normal distribution, then you need to find the probability that X is between A minus 0.5 and A plus 0.5. Okay. If you want to find a probability that the number of successes is larger or equal to A, then if you want to use a normal distribution, then you need to find probability that X is strictly larger than A minus 0.5. If you need, let's say, R, number of successes, strictly larger than A, okay, then you need probability that X is strictly larger than A plus 0.5. If you need probability that the number of successes R is less or equal to A, okay, then if you want to use the normal distribution, then you're going to need to find probability that X is strictly less than A plus 0.5. Okay, and if you want to find probability that the number of successes R is strictly less than A, then that will be the probability of X less than A minus 0.5. Okay. So let's do an example so we can see what I'm talking about here. So let's say baseball players batting probability is baseball players batting probability is, let's say, 32%. Okay, and let's say we want to find the probability that the player will get at most, let's say, 26 hits in 100 times at bat. Okay, the player will get at most 26 hits in 100 times. Okay, so he's gonna try 100 times. Okay, at bat. So, first, this is a probability distribution because either the player is gonna get a hit or it doesn't, right? Or he doesn't. So probability of success here. So success here is that the player gets a hit, right? Success here. Okay, we get a hit at the bat. Okay, so what's the probability of success here? Well, first, number of trials. So the baseball player is gonna try 100 times. So the number of trials N here, capital N here. So the number of trials here is 100. Right? What's the probability of success? So what's the probability that the player gets a hit at the bat? Well, we know that baseball players' batting probability is 32%. So the probability that the player gets a hit at a bat is 32%. So the probability of success is 32% or 0.32. Okay, so what would be the probability of failure here? Remember, P plus Q is always equal to 1, right? So P plus Q is equal to 1, so then Q must be equal to 1 minus P. Okay, so it's 1 minus P, so 1 minus 0.32, so that's 0.68 or 68%. That's the probability of failure here. Okay. So that's my binomial distribution. So the question here is, again, what's the probability that find the probability that the player will get at most 26 hits, right? So again, number of success here. So R, remember R, that was the number of successes, right? That's the number of successes here. Okay, so we need to find the probability that the player will get at most 26 hits, right? At most. So it means it's less or equal to 26. Okay, at most 26, it means it's less or equal to 26. So we want to find the probability that the number of successes, the number of hits, right, is less or equal to 26. Okay, so this is less or equal than 26, right? So that's the probability we want to find, right? Of course, we can use, the formula for the binomial distribution, but the thing here is that the numbers are kind of large, right? 26, that's a lot. This is supposed to be like P, probability that R is 0 plus R, probability that R is 1 plus probability that R is 2 plus probability that R is equal to 3 plus etc plus probability that R is 25 plus probability that R is 26, okay? So that's a lot, right? That's too long, right? It's too long. Right, so the idea is use binomial, we can approximate. So the idea here, instead of using the usual formula for the binomial distribution, we can try to approximate this binomial distribution using a normal distribution. So here we're gonna use a normal distribution. Okay, so we can approximate this. Again, use the central limit theorem to approximate this binomial distribution using a normal distribution. So, and here it's okay to use it because we said we need, remember here, there are two conditions here. If n times p is larger than 5 and n times q is larger than 5, then we can use a normal distribution. Okay, so we need n times p to be larger than 5 and n times q to be larger than 5, right? So let's compute this. So here, it's okay to use the normal distribution because if you compute n times p, so that's 100 times p is, we said it's 32% or 0.32, right? So that's equal to 32, which is of course larger than 5. And the same here, n times q, that's 100 times 0.68, so that's equal to 68, which is larger than 5. So here, it's okay to use a normal distribution, okay? So let's use a normal distribution. Now, what's the... So we're gonna use normal distribution. So we're gonna convert our R. Where is it here? So here we're gonna use a normal distribution. So again, we need to find the probability of successes R is less or equal to 26, right? That's the question here. So R is less than or equal to 26. The number of hits that the player will get at most, 26 hits, right? So our number of successes here less or equal to 26. So now if you want to use the normal distribution, we said because there's this correction for continuity. So R, you see here, R less or equal to, so here A, that would be 26. So this A here would be 26, okay? So R less or equal to 26, then we're gonna need R or X, then we're gonna try to find the probability that X is larger than 26 plus 0.5, okay? So here, because of this correction to continuity, okay, so that will be equal to P of X less, okay, so we said it's less, so here R, which is 26, less, R is less than A, so A is 26, right? So R less or equal to 26, so that will be X less than 26 plus 0.5, so X less than 26 plus 0.5, so that's P of X less than 26.5. Okay, so what's the probability that X is less than 26 or 0.5? So now we're going to use the Z-score. So remember, Z is equal to X minus mu, the mean, over the standard deviation, right? So what's the mu here? And what's the standard deviation? Well, we said mu, the standard, the mean is equal to n times p, and the standard deviation is square root of n times P times Q. So mu is n times P, and the standard deviation sigma is square root of n PQ. So that will be equal to, so the mean is n times P, so that's 100 times 0.32. So that's equal to 32. And sigma, that's square root of 100 times 0.32 times 0.68. So that's equal to actually 4.66. So my z here is going to be equal to x. So what's x here? So it's 26.5. So it's 26.5 minus mu, that's the 32, over the sigma, the standard deviation, which is square root of npq, that's 4.66, and that will be equal to negative 1.18. So my z here is negative 1.18, so that's probably that z is less than negative 1.18. So z is less, so that's if you graph your distribution, here's your distribution. Here's, let's say, negative 1.18. So z is less means that's the area to the left, right? This is left, so this is less. So that will be the left of negative 1.18. So here's my negative 1.18, right? So and I'm looking to the area to the left of negative 1.18. So that's exactly the value given by the table of the standard normal distribution. So here I'm gonna use the table, and so here this is table of the standard standard normal distribution, and that will be equal, if you use the table, check the table, for z equal to negative 1.18, so that will be 0.119. So the answer is actually 0.119, so that's 11.9%. Okay, so the answer, so probability that R, the number of hits, R, is less or equal to 26, is actually so 0.119, so that's 11.9%. Okay. So here it's you see, guys, here it's really important. So here, like in the question, it says at most 26 hits, which means it's less or equal to 26, right? And then so once you write this less or equal to 26, then you have to be careful when you use this correction to continuity. So if it was strictly less, then that would be x less than a minus 26 minus 0.5. But here it's less or equal, so that would be 26 plus 0.5. Okay. Okay, guys, let me now just finish last thing here with the proportion of successes. We can approximate the distribution of proportion of successes using normal distribution. So suppose now we repeat a binomial experiment with n trials over and over. Okay, so suppose we repeat a binomial experiment with n trials over and over. So this is sort of, this is like analog to the normal distribution of the mean x bar. Okay, so for each, so what we're gonna do now, for each n trials, we're gonna record the proportion of successes. So for each n trials, so we record the proportion of successes. So proportion of successes is denoted by p hat. P hat, that's actually R, the number of successes over number of trials. Okay, so it's kind of like analog of the, the X bar in the, in the normal distribution. So here P hat, so it's R over N. So the thing is, if again, if NP is larger than 5 and NQ is larger than 5, then P hat can be approximated with the normal distribution. Then P hat can be approximated with normal distribution. With mu, the mean, so mu of P hat equal to P, and the standard deviation of P hat equal to square root of PQ over N. Okay, so let's do an example. Okay, let's say the crime rate in Denver is, let's say, 11.1%. Okay, and let's say you have a building has, say, 50 residents. Okay, so suppose that the number of successes R, so R is represent the number of victims of a crime. Okay, so R represent, that's the number of success. So let's say that R represents the number of victims of crime. Okay, so let's consider the proportion of the victims. So let's consider P hat equal to R over N. Okay, so that's R over, so we have 50 residents, right? So R over 50, that's the proportion of victims in the building. Proportion of victims of a crime in the building. Okay, so the question, can we approximate the distribution of P hat with the normal distribution? Can we approximate the distribution of P hat with a normal distribution? Okay, so again, we said, so that you have this proportion of successes P hat, and if N times P is larger than 5 and N times Q is larger than 5, then yes, we can approximate the P hat with a normal distribution. So here, in this problem, what's the number? What's N? The number of trials? Well, we have 50 residents, right? That's N. So this number here, this is the number. That's the number of trials. Okay. So what's the success here? So R. the number of successes here represents the number of victims of a crime, okay? And we said the crime rate in Denver is 11.1. So the success here, probability of success, probability that the person is a victim of a crime is 11.1. So that's the probability of success. So that's P, okay? So here N is equal to 50 because we have 50 residents in the building, right? P, that's probability of success. And again, success here, R represents the number of victims of a crime. And the crime rate, so the probability that the person is a victim of a crime is 11.1% in Denver, right? So that's 11.1%. That's the probability of success. So what will be the probability of failure? So what will be the probability that a person in Denver is not a victim of crime? So that's, again, it's 1 minus P, right? Again, P and Q adds up to 1. So that's 1 minus 0.111. So that's 0.889. Okay. So can we approximate a p hat with a normal distribution? Remember, guys, the condition here is that, so NP is, if NP is larger than 5 and NQ is larger than 5, then yes, we can approximate the p hat, the proportion of successes, proportion of people or proportion of residents victim of a crime in the building can be approximated with a normal distribution. So let's see, NP is, so that's N is 50, P is 0.111, so that's equal to 5.55, so that's larger than 5. And Q, so that's 50 times 0.889, so that's 44.45, larger than 5. So yes, so we can approximate, so P hat can be approximated with the normal distribution. And what will be the mean and the standard deviation? So with the mean mu, so the mean of p hat would be, so we said the mean of p hat would be equal to p. And the standard deviation of p hat, the proportion of successes, is pq over square root of pq over n. So p hat here, the mean of p hat would be just p, and p is 0.111. And standard deviation of p hat, so that would be square root of pq over n. So that's square root of, so 0.111 times 0.889 over 50. Okay, so then if you do the computation here, so that will be 0.044. So that's the standard deviation of p hat, or the proportion of successes, or if you want, that's a proportion of residents victims of a crime in the building. Okay. Well, guys, I guess you can find more examples in the lecture notes. And again, if you have any questions, just send me an email. Okay, bye. Thank you. See you next time.